Okay, so now you know all about OU factorization in terms of how to do it. This is just an extra page on sort of defense for why this will work in general. It's not a complete proof or anything, but it's just sort of an explanation with a general 3x3 example. So it's kind of this magical thing happens, right? These multipliers all fit together. We don't have to do any actual multiplication once we understand it. The Lij's will just go in the right place, put ones down the diagonal. There's your L matrix. Okay, so why does this work? So we do row reduction. It uncovers U. We start with A, it uncovers U. We record the multipliers as we go along. And then we can say, oh, we have A is L times U. Multipliers go into the L. The U we uncovered. So U is not obvious, right? So the pivots are not obvious. They're not evident at all in A to start with. The first pivot might be, but something you have to uncover, and the same with the multipliers. But on the other hand, what this says is once you have U, A is easy to build, if you know that, right? There's a simplicity of the way it's built because L is pretty simple. L is a lower triangular matrix. Okay, so I'm just going to read through this. I felt like I needed to write it out first. So we've got this product, at least for a 3x3, where we multiply the inverses of the elimination matrices, which encode row operations. We reverse the order. We know they're simple. All we do is we take the elimination matrix, which is almost the identity matrix, with a minus Lij in the ijth entry, and we flip it to plus Lij. And then you'd think maybe multiplying it might make a big scramble, but actually it combines in a very naive, simple-looking way. The multipliers just end up in the right spot because we chose things carefully, wisely, shall we say? And so why is that? Why is that? So just a couple of words. So as we uncover U, we're doing our row operations. If we think about what happens there, we only ever use rows of U to make new rows of U. This may sound a little confusing, right? So we start with A, and let's just ignore row swaps to start with. Start with A. Our first row of U is the first row of A, so that we've already got that. But then when we start to modify along the first column of A, we're trying to make zeros there, we can say, well, we're actually using row 1 of U to subtract from A's rows. So then we've done all this, and then row 2 will be finished, right? We've got a 0 here, row 2 will be finished. There's nothing more we can do with it. We start using that to clean up more zeros, this time in the second column. We use row 7 to clean up rows in the 7th column, so on. The row that we're using to do that cleaning up is a finished product for U, right? So once we've uncovered it, so we have the finished U row. So, and I'll have some more things here. So that suggests that when we go back to make A, right, because we've only modified rows lower than the row we're working on, it suggests we'll end up with a triangular way of combining this new matrix U's rows to get back to A. Okay. If we were using everything to get rid of it, right, that'd be a big, messier matrix. So let's maybe just go to this piece here. So this is really just writing out what row operations do for a 3x3 example. So row 1 of U, as I said, is row 1 of A. Again, ignoring row swaps. Row 2 of U, well, we start with row 2 of A and we subtract the first multiplier, L21 times what is now row 1 of U. We're interpreting that way, it's really row 1 of A. And then row 3, this is some complexity arrives here, row 3 of U. Well, we start with row 3 of A. Of course, we have to start with that. And if you think back, well, we subtracted a multiplier times the first row of U, right? That was to make a 0 down in the corner. And then to make the 0 next to it, we subtracted L32 times row 2 of U. Important that it's U. And if you look at this, right, so as I said, U's final form is opaque. And you can see what's going on here, right? Because we start with A. But to get to the rest of U, we have to make U systematically. So to get to the 8th row of U, to finish that, we have to have made the 1st, 2nd, 3rd, 4th, 5th, and 6th, and 7th. So U's rows depend on all the rows above. All right. So we can turn this around then. I'm just going to take these equations and put all of the rows something of A and all of the rows something of U on one side. And so, for instance, this will come over here, and then I'll swap them around, and this would come over here as well. Okay, so all the U's are on one side. So the first line just reads row 1 of A is 1 times row 1 of U, and that is this line here. That's what L does here. This one, row 2 of A, well, it's just the second row of U plus L21 times row 1 of U, and that is this piece. Last thing, right, so row 7 of A is row 7 of U plus 6 multipliers times their respective rows, and so row 3 of U, that's this one here, L31 times row 1 and L32 row 2, so those pieces are all sitting in there. So you have to sit down and think about this for a while to believe it, but this explains why we end up with such a simple expression for what is a combining matrix, which I've written here. It's a combining matrix. A is something times U. And it makes sense that it's something times U. We took A, we messed around with its rows, we end up with U. We haven't deleted rows. We shouldn't, we shouldn't have lost information. We're just combining them. So we should be able to rebuild it. The fact that it's so simple comes from thinking through the row operation process and then undoing it. So that's just a small piece to add, but you should be able to do row reduction, and then you should be able to, at least for the time being, force computers to do it if need be.